Good morning, viewer. Welcome to our Globe TV of some breaking news. Our researchers from the National University of Singapore and collaborators have developed a predictive design strategy for creating graphene-like molecules with multiply interacting spins and enhanced resilience to magnetic perturbation, and opening new avenues for molecular scale quantum information technologies and next generation spintronics. The research team was led by Professor Lu Xiong from the NUS Department of Chemistry and US Institute for Functional Intelligence Materials, together with Professor Wu Zisen from the NUS Department of Chemistry and international collaborators, including key contributor Professor Pavel Zelinek from the Czech Academy of Science in Prague. Magnetic nanographenes, which are molecules composed of fused benzene rings, were of growing interest of quantum technologies because they can host unpaired electrons or spins, and that may be used to store and process information. Unlike conventional magnetic materials based on metal atoms, these carbon-based systems for chemical versatility and long spin coherence times. So, engineering a single molecule that contains multiplied strongly coupled spins in stable and controlled manner remains a major challenge. Building on a well-known molecular structures called Clar goblet, the research team synthesized two extended nanographenes, the formula C62H22 and C67H26, using atomically precise on surface chemistry with their structures and properties characterized by scanning approach microscopy. Viewers, by changing the molecular shape in two different ways through lateral and vertical extension, the researchers were able to independently control both electron interaction and the number of zero energy modes. Although both molecules host four unpaired spins, these arise from distinct mechanisms. In one molecule, the spins are driven entirely by the geometry of the carbon framework. In the other, they result from the combinations of geometric effects and enhanced interactions between electrons. Professor Lu said, our work establishes a clear structure, a property relationship in hourglass shapes nanographenes through combined experimental and theoretical investigation. So, this advances from unprecedented control over the magnetic properties of molecular materials, opening new possibilities for molecular qubits and quantum simulators based on carbon platforms. The research team also compared the magnetic resilience of the two tetra radical molecules using scanning probe microscopy measurements with a magnetic sensor. Although both molecules contain four strongly correlated spins and they behave differently under external magnetic perturbations, one molecule showed much stronger resilience, meaning its quantum state was harder to disrupt during measurement. So, this robustness is especially important for applications such as molecular qubits, where preserving fragile quantum states is essential. We have this exclusive report.